Hi everyone! In this video, I'm going to demonstrate how to graph a natural log function without using technology. So the good news is that all logarithmic functions, they can be graphed just like we've done in the past by identifying the parent function and then identifying transformations. So in this case, we have f of x is equal to negative natural log of x plus 2. Please be careful when you say this function. You don't want to say ln. Even though I know you see the letters ln, you really do want to recognize that that means natural log and then read it that way. So f of x is equal to negative natural log of x plus 2. So first you want to recognize that the negative out in front and this plus 2 are both going to cause transformations. So if we initially ignore those, what we have left is y is equal to the natural log of x. And this is going to be our parent function. So the first order of business is graphing this parent function. And if you're not sure what this graph is going to look like, then I'm going to suggest that you rewrite this logarithm in exponential form. Now, to do that successfully, we have to remember what it means to have a natural log. So a natural logarithm is just a logarithm with a base of e. So first, I'm actually going to rewrite this as y equals log base e of x. So I'm recognizing that the base is going to be e. And remember, e is that irrational number, very much like the number pi. E is approximately 2.7. I always say 2.7-ish. So this is log base 2.7 of x, essentially. So therefore, if we're going to rewrite this in exponential form, remember we start with the base and then we loop around the equal sign. So e raised to the y power is equal to x. So the exponential form is going to be e to the y power is equal to x. E to the y equals x. That's what we're going to try to graph. And we'll probably get a start on this by making a table. Now, normally we fill up the left-hand side of our table with x values, but in this case, it would actually be much easier for us to choose y values because y is the exponent. So it's easier to compute powers of e. So therefore, we're going to fill up the y side of our table. So from negative 2 to 2 on the y side of our table. Therefore, we're going to first compute e to the negative 2 power. Now, don't be scared. I know you often want to just run right to your calculator here, but we're trying to do this without our calculator. So let's think through this. A negative exponent means we are going to change this to 1 over e squared. So I don't expect you to know what 1 over e squared is actually equal to. But what I do expect you to know is if e is 2.7, approximately, we'll just use 2.7 as the estimate, then this is basically like 1 over 2.7 squared. So let's just round a little bit to think through this. If 2.7, let's say, rounds to 3, so this is really something close to 1 over 3 squared, and 3 squared is 9, then we would expect the output to be something close to 1/9. And what we need to know about this number is it is a positive value and it's small. It's very close to 0. So I will even just write close to 0 here. I don't expect you to know the decimal. I just want you to know that this is a positive number and it's going to be a value close to 0. All right, let's think through this again with negative 1. So e to the negative first power is going to be 1 over e. And again, that's going to be approximately 1 over 2.7-ish. So again, thinking of that like 2.7 is close to 3, that'd be close to 1/3. Again, this is a small number, it's a positive number, and it's close to 0. So I'm just going to write close to 0. E to the 0 power we should know. E to the 0 is 1. And e to the first power we know is approximately 2.7. So we would expect to have 2.7. So if you were graphing this by hand, to be honest, these are the two coordinates I would expect you to have on your graph. I'm going to go ahead and graph those now. So we're looking at 1, 0, and then right 2.7. You'll just estimate that and up 1. Now, if you're graphing this in Alex, the nice part about Alex is you don't have to enter the coordinate as 2.7, 1. You can actually enter it as e, 1. So in Alex, you can actually type E, and it knows that E is approximately 2.7, and it's going to plot that for you. So on paper, you'll estimate 2.7. In the computer, you'll go ahead and type it as E. If we move on to y equals 2, then we're computing E squared. And again, we could estimate that. We know that E is 2.7, so it's between 2 and 3. So if you think about 2 squared is 4 and 3 squared is 9, then we know we're going to have a value of E squared, something between 4 and 9. And I'm okay with you using your calculator one time if you're not sure what E squared is. If I go to my calculator, E squared is about 7.4 approximately-ish. But again, I really don't even require that value on paper. I would only expect you to have the coordinates 1, 0, and 2.7, 1. I will go ahead and graph 7.4, comma 2. And then we need to remember that all logarithmic functions have a vertical asymptote. So this graph is going to go down forever, and it's going to hug that y-axis. And then it's also going to continue to the right forever. So I recommend that you go ahead and graph in the asymptote. I always choose a different color. So this parent function has a vertical asymptote, and that vertical asymptote is x equals 0. Now, if you wanted to verify these coordinates that we started with, the ones that we didn't actually find exact values for, we said we have an x value that is close to 0 when y is negative 2. So imagine that's like going to the right just a little bit from the origin and then down 2. So that would coordinate with this point here. And same thing, close to 0 and negative 1 would be like going from the origin right just a little bit and down 1. So you can see those values do match on our graph when we recognize that there's a vertical asymptote. Now let's apply our transformations. So looking back at the original function, f of x is equal to negative natural log of x plus 2, we have a negative out in front. So we are multiplying our natural log of x by a negative. So that is going to cause the y values to become negative. And when the y values become negative, that is going to be a reflection over the x-axis. So the negative out in front is a reflection. We're going to reflect over that x-axis. And then we have to take a look at this plus 2. Now, it's really important to notice that there are no parentheses here. If I wanted that plus 2 to be with the x, I would have had to put parentheses to indicate that for you. But there are no parentheses here. So that means that that plus 2, it is not a quantity being held with the x. So you almost can imagine this like we have natural log of x, and then we have the plus 2. Think of this plus 2 as on the outside of the natural log of x graph. Therefore, it's impacting the y values, and our y values are going to become 2 units larger, which is going to shift our graph up 2. So I'll go ahead and do this in 2 steps. So my first step is going to be my reflection. I'm going to do that in blue for you. So if we reflect across the x-axis, the vertical asymptote doesn't change. And don't worry about these little coordinates here that had the fractional x values, because we're just going to use the vertical asymptote as our guideline. So we're really only going to worry about these coordinates, these 3 coordinates here, and we'll reflect all 3 of those. Now, the x-intercept of 1, 0 is going to remain 1, 0. Then our coordinate, which was 2.7, comma 1, is going to reflect, so it'll be 2.7, comma negative 1. And then our coordinate, which was 7.4, comma 2, is going to jump down across the x-axis, and that becomes 7.4, comma negative 2. So again, just with those 3 points, we can see that we're going to have this nice smooth graph. It's still going to hug that asymptote, and it's still going to be going right forever. So this blue graph is the reflection across the x-axis. And then we want to take that blue graph and we want to move it up 2. Now notice, if we go up 2, this asymptote still remains the same. If I move a vertical line up, it remains the same vertical line. So we're really just going to take our x-intercept and shift it up 2. And then you're just going to take our 2 points and shift them all up 2. So that last point, the one that was right here, it really is going to end up right on the x-axis. It's going to be our x-intercept. and then we maintain that same shape, hugging that vertical asymptote, and then again going to the right forever. So this graph that I have in green, I'll mark as f of x, is essentially my final answer. So asymptote is still x equals 0. Vertical asymptote hasn't changed. Looking at this graph, the domain, remember, is from left to right. We go leftmost to rightmost. And this graph is never going to intersect that vertical asymptote. So our domain will be all of the x values from 0 to infinity. And I'm using a parenthesis on 0 because it's not going to intersect that vertical asymptote. And then our range, which is lowest to highest, all of the y values. This graph goes down forever and also goes up forever. So the range will be all of the y values from negative infinity to positive infinity. One last thing before we move on is always check your graph by figuring out the domain algebraically. Because we just did our domain utilizing the graph, but if we had made a mistake in our transformations, we could catch that mistake if we thought about the domain algebraically. So looking back at the original function f of x, notice, remember, x is here inside of this logarithm. We call that the argument. So in this case, the argument of this logarithm is just a plain x. Remember, this plus 2 is not in the natural log. It's not part of the logarithm. It's essentially on the outside, as I mentioned before, because there's no parentheses. So we need to remember that when you have a logarithm, any type of logarithm, doesn't matter whether it is a natural log or a logarithm with a different base, the argument must be positive. So that means that x must be greater than 0. We can never take the log of a negative number, and we cannot take the log of 0. So that means if x is equal to 0, then our domain certainly is from 0 to infinity, and that sort of confirms the domain that we had earlier when we utilized our graph to figure out the domain. So it's a nice way of checking to see whether we did our transformations correctly.